Assalamu alaikum. Welcome to the lecture 5 of Unit First. Now, after power diode, we are discussing another power semiconductor device, that is thyristor, or we simply call it as SCR, that is silicon controlled rectifier. After the invention of SCR by Bell Laboratories, as discussed in previous lecture, many semiconductor devices with similar characteristics were developed. These semiconductor devices include triac, diac, silicon control switch, programmable unijunction transistor, GTO, and extra. This whole family of semiconductor devices was given the name thyristor. Define the thyristor as it denotes a family of semiconductor devices that are used for power control in AC as well as in DC circuits. The silicon control rectifier is the most widely used device. That's why its name has become synonymous with SCR. The word thyristor is derived by a combination of letters THYR from the thyrotron and ISTOR from the word transistor. That means this thyristor can also be defined as that it is a solid state device like a transistor and has characteristics similar to that of a thyrotron tube. You have already studied transistors in your previous semesters, so I'm not defining that transistor here. And this thyrotron tube that's not in your syllabus is basically a gas filled tube that's used as a high power electrical switch and controlled rectifier. Here I'm discussing only this thyristor. That means the transistor they have already you have already studied them in your previous semesters, and this thyrotron tube is not in your syllabus. Now the construction of silicon controlled rectifier or SCR. It is a four-layer, three-junction PNPN semiconductor device having three terminals: anode, cathode. K represents here, A represents anode, K represents cathode, and G represents the gate. Or we can say here we have alternate layers of P and N materials, which results in the formation of three junctions: junction J1, junction J2, and this junction J3, where basically we can say the junction is made when the two materials are brought in physical contact with each other. Here, all the four layers have different doping levels. Here, the outer layer we can also represent it by P1, this N negative by N1, this P by P2, and this N positive by N2. That means this P positive or P1, it's highly doped. That means here, because of this positive represents the high doping level, and similarly the outer N2 is represented by N positive. That means the doping level is here. The doping level is very high. While as this P represents this inner P, which we call as P2 also, it's normally doped. Here, this N1 or this N negative region is very wide and lightly doped. That's why it's represented by N negative. Mm, the low doping this low doping provides high forward and reverse voltage blocking capability of SCR. Moreover, this is a circuit symbol of SCR having the three terminals. This just like a diode with one more feature, that is this gate terminal. That means this is anode, this is cathode, this is represented by gate G. This terminal is represented by the alphabet G. This represents anode to cathode voltage. SCR, it's a unidirectional device. That means it allows the flow of current in only one direction, that is from anode to cathode. Moreover, this is also a bipolar device. That means it blocks both positive, that means forward voltage, and negative, that is reverse voltage, and allows only unidirectional current to flow through it. This is available, this silicon control rectifier is available in high, because the power handling capacity of these power semiconductor devices are very high, or we can say that the it's available in high voltage and current ratings from 1 ampere to several kiloamperes, and from few tens of volts to several kilovolts. Thyristor has a thyristor has three basic modes of operation. One is reverse blocking mode, forward blocking mode, and forward conduction mode. In order to explain the IV characteristics of SER, we should explain, we must know about these three modes of operation, that is reverse blocking mode. In this mode, the SER is also in off state. In this mode, forward blocking mode, the SER is also in off state. The only mode in which SER is in on state is this forward conduction mode. This is the elementary circuit diagram. This is the elementary circuit diagram of this this is the elementary circuit diagram by which we are going to explain this IV characteristics of SER. This is simple SER having three terminals: anode, cathode, and gate. Here, since for on state we need the control signal, and here we are applying the gate current. That means to any current to flow in the circuit, we need the voltage. This is the voltage VG, which represents the gate voltage, and here we are using one variable resistor, that is the resistance RG. We can here this we can get this current IG by turning on and off of this switch. This is the load resistor that we have connected in the circuit, and this V represents the source voltage that we are applying across the anode cathode terminals of the circuit. That means the main elementary circuit diagram of this SCR, it represents the source voltage and the gate voltage, from which we are going to obtain that variable gate current, which is the which this gate current is basically a control signal for the SCR to remain in the on state. During the reverse blocking, the first mode of operation, that is the reverse blocking mode. Since its name is reverse, that means reverse blocking mode, it means that we are applying the reverse voltage across these anode cathode terminals. This is the first I'm explaining the reverse blocking mode. This is the PNPN device, that is SER. Here this is the P positive and negative, P and positive SER. Across the anode and cathode terminals, we have applied a reverse voltage. That means this anode is negative and this cathode is positive. And across this gate terminal, we are not applying any gate current. That means I am writing here that gate current is equal to 0. Now, since it's a three-layer device junction, we have three-layer junction J1, junction J2, and junction J3. When a reverse voltage is applied, that means this junction J1 here, here across the junction J1, we have two layers, that is P and N negative. This P is connected to negative, and this N negative is connected to the positive. That means this junction J1 is reverse biased. Junction J2, across the junction J2, we have two layers. That means this N negative is connected to negative, and this P is connected to the positive. That means this junction J2 is reverse biased, and across and this junction J3, we have two layers, that is P and N positive, When it's reverse bias, that means this junction when it's connected to the when it's connected to the battery reverse voltage, we can say this junction P is connected to negative, and this junction this layer P is connected to the negative, and across this junction J3 this layer N positive is connected to the positive. It again means that this layer junction J3 is reverse bias. That means when we are applying a reverse voltage, junction J1 and J3 are reverse bias, and the only junction that is forward bias is junction J2. I am representing this by this. That means this J1 it's off state. This junction J1, and that means this whole voltage is across the two junctions, that is junction J1 and junction J3. And while as this junction J2, this is in the that means this there is no depletion layer across this junction J2, and the depletion layers are present across junction J1 and J3. Now since we know that across this junction J3, uh, we have a highly doped two layers, while as across the junction J1 we have one highly doped layer, and the another layer is very weakly doped. That means we should keep it in mind that when a reverse voltage is applied across this junction, across this anode to cathode voltage, the depletion layer across the junction J3 and the depletion layer across the junction J1, both the depletion layers are removed as soon as this reverse voltage is increased. But we should keep in mind that the depletion layer across this junction J3 removes or depletes quickly as compared to the depletion layer across the junction J1. This is because of the two highly doped layer across the junction J3. This depletion layer is removed quickly as compared to this junction J1, where the one layer across the junction is very lightly doped. But that means we should keep it in mind that junction J1 has high reverse blocking capability, has high reverse blocking voltage capability as compared to this junction J3, because of this lightly doped layer across this junction J1. We should also keep it in mind that our reverse voltage should be less than this breakdown voltage, because at this breakdown voltage at the breakdown voltage at the breakdown voltage a large amount of current flows due to the avalanche effect, which may result in the heating of the junctions, or it may cause the serious damage to the SCR. And that means, or we can say, during this reverse blocking mode, our SCR also remains in the off state, just like our diode. That means when we are applying the reverse voltage, a small amount of leakage current flows until and unless when our reverse voltage exceeds this breakdown voltage, a large amount of current flows, which may destroy our SCR. And this current we call as reverse blocking current. This voltage, which is called VBR, this is the reverse breakdown voltage, and this mode we call as reverse blocking mode. In this mode, the SCR remains in the off state. Now the second mode of operation, that is forward blocking mode. In forward locking mode, we are applying the forward voltage, that means forward biasing, across anode and cathode terminals. And here also, in this blocking mode, also no gate current, or no control signal is applied to this circuit. In this forward blocking mode, this junction J1 it becomes this junction J1 becomes forward bias, because this P is connected across this junction J1, this P is connected to the positive, and N negative, or this P positive. This is basically not only P, this is P positive. This is just a mistake in the diagram. This P is connected to the positive of the terminal, and this N negative is connected to the negative. That means the junction J1 is forward biased. In case of junction J2, this N is connected to the positive and this P is connected to the negative. That means this junction J2 is a reverse biased. And this junction J3 is also forward bias. That means this P is connected to positive and this N positive is connected to the negative. That means during this forward blocking mode, this junction J1 becomes forward bias. It behaves like this. Junction J3 is forward bias, while as this junction J2 is open. That means again in forward blocking mode also the SCR is in off state because of this open junction. That means we can say that this SCR has this junction J2 has forward blocking capability. That means this is the characteristic in this forward blocking mode. Then that means since this is open circuit, this behaves like the open circuit because of this junction J2, which is reverse biased. A small forward current flows. This is represented by this red one is represented by small forward leakage current, and this represents at this M point. This we call it as VBO, that is breakover voltage. That means the forward blocking capability of this junction is up to this breakover voltage. Once the reverse voltage or this once this forward not reverse voltage, once this forward voltage exceeds this breakover voltage, avalanche breakdown occurs across this junction J2, and a large amount of current flows through the device. Increasing this forward voltage beyond this breakover voltage is not the safe method of triggering, or by triggering we mean turning on of SCR. Because once we increase the voltage over this breakover voltage, the junction J2 this junction J2 breaks over, and this results in the large amount of current which may cause damage to the SCR. Thus, increasing this forward voltage over this breakover voltage is not the safest method of triggering. We are going to in the next lecture, we are going in the next slide. We are going to we are going to study the safest method of triggering or turning on of SCRs. I'm going to explain in that slide. Now the next mode, that is the forward conducting mode. In the forward conduction mode, we are applying one more thing one more thing, that is the gate current. In the previous mode, that is forward blocking mode, we are applying just the forward voltage and no gate current, while as in this forward conduction mode we are applying the forward voltage plus the gate current. To show this gate current, I am showing here. This is the gate voltage across the gate cathode terminals, because current flows in the circuit only when there is some voltage across the terminals across the terminal. Just like here, we have applied the gate cathode voltage, and now I am showing this gate current to the inner P junction. That means in this forward conducting mode, the junction J1, just like your forward blocking mode, this is forward bias. This junction J3, like your forward blocking mode, is forward bias, and this junction J2 is reverse bias. I mean, this is forward bias. That means there is no depletion layer across the junction J1. There is no depletion layer across the junction J3. The only depletion layer is present across this junction J2. But that means this layer behaves like a capacitor with the stored charge. Now, by applying this control signal, or here you can say this gate current, we are neutralizing the stored charge across the junction J2, which results in reducing the depletion layer. That means during this if I am representing this as the gate current, if Ig1 is represented by the gate current, and if I am applying gate current Ig1, then I am saying, by applying this Ig1, this Ig1 neutralizes the stored charge across junction J2, and this depletion layer is removed before the forward before the voltage forward voltage reaches this break over. This is the Ig1, and here I am showing this breaking over characteristics, and resulting in the forward current like this. That means higher the amount of gate current, that means Ig3 is greater than Ig2, Ig2 is greater than Ig1. Quickly quickly this diode reaches its study or reach its on state. This represents this represents that means in SCR, during reverse blocking mode, the SCR is in off state. During forward blocking mode, since we are not applying any gate current, we are just applying forward voltage, your SCR is turned off. That means your SCR is turned only in this forward conduction mode, where you are applying a gate current. Higher the value, the typical gate current magnitude that we are using are of the order of 20 to 200 milliamperes. We should also keep it in mind that once the SCR is turned on, by applying a gate current, we cannot turn it off. We cannot turn it off by just removing the gate current. That means once the SCR is turned off, it remains in its on state or latching state. Until and unless a reverse voltage is applied. That's why we are saying that SCR is a semi-controlled device. That means it's only on is controlled, while as it's off is not controlled. It can be turned on by cutting the power supply, or you can say by applying the reverse uh, reverse voltage. However, we should keep it in mind that if gate current is reduced to zero before the anode current attains a value called the latching current, that means here we have two values. One is the latching current, another is the holding current. Means if gate current is reduced to zero before the anode current attains a value called IL, that is before it attains the value latching current, the thyristor will turn off again. This means that this latching current is defined as, or we can say this latching current is the minimum value of anode current which SCR must attain during the turn on process to maintain the conduction. Even one more thing is that is this I represented by this II, that is the holding current. This latching current is linked with the on of the SCR. This is linked with the off of the SCR. That means this holding current um, it is the minimum value of anode current below which SCR must fall. It's the minimum value of anode current, and below it is the minimum value of anode current, below which this anode current must fall for turning off of the SCR. This latching current is higher than the holding current. That means we have two we have two currents associated. This latching current is associated with the on state. It is the minimum amount of anode current that SCR must attain for the turning on of SCR, even if the gate signal is removed. And this whole current is the minimum value of the anode current below which it must fall for turning off of the SCR. uh, or in or If we sum up all the three modes of operation, that means this is the reverse blocking mode, this is the forward blocking mode, and this is the forward conduction mode. In the reverse blocking mode, when cathode is positive with respect to anode, when cathode is positive with respect to anode, SCR is turned on. When SCR is turned off, junction J1 and J3 are reverse bias, and junction G2 is forward bias. Another is forward, and here the current is just like that leakage current, until and unless if the reverse voltage increases this breakdown voltage, then this junction then the junction breakover occurs across this junction J3, and this results in the large amount of current which may destroy our SCR. Another is the forward blocking mode. In this forward blocking mode, anode is made positive with respect to cathode, and no control signal is here applied. Junction J1 and J3 are forward bias, and junction J2 is reverse bias. Since no gate current is applied, one method of triggering, which is not the efficient method of triggering, is by increasing this forward voltage over this breakover voltage. That means up to this, if we are increasing this forward voltage up to this breakover voltage, it remains in the off state. If it remains in the off state until and unless we are applying some gate current or some control signal. Another mode of that means in this mode of operation also SCR remains in the off state. Another mode of operation is the forward conduction mode. That means in this mode, it is also forward biased. Junction J1 and J1 and J3 are forward biased, and J2 is reverse biased. One more extra thing that we are adding to this is that gate signal, which is the efficient method of triggering. By applying the gate current, this by applying that means I am representing this by this. By applying the gate current, the depletion layer across this junction J2 gets reduced, and it quickly changes the state from off to on state. Similarly, greater the amount of gate current, lesser time it will take to turn on.